Thank you.
Okay.
Yeah, so this will be a little bit different than many of the other talks today. But this is my first time here, so I want to say thank you for the opportunity to come and putting together such a great workshop. So, I'm a grad student at Rutgers University, and this is what I'll be talking about. So, dark matter is the foundation of almost everything that we're doing. And despite that and all of its successes, there's been a decade-long, bit more than that, search for some new particle, and that's come up empty. All of the positive things that we know about dark matter come from astrophysics. So can we do a little bit more to help the search along? So I'll be talking specifically about the direct detection search for WIMP dark matter and what we can say about that. So first, just how do you go about searching for WIMPs? Well, you take some stable nucleus, sit it in a very isolated place, hope dark matter and nature is nice to you, comes in and hits your detector, and you get a signal that you can disentangle from some background. So the expected detection rates are something like 1 kilogram per year one signal per year per few hundred kilograms of detector material. So not very much, and it's very easy to wash away. So like I said, there's been a very long search for this, and this is the results as of 2014. Some of these lines have moved down a little bit, and I'll just draw your attention. So WIMP nucleon cross-section versus dark matter particle mass. The dark matter particle mass, as long as it's a WIMP, is probably irrelevant for most of our simulations, so you don't have to ever worry about that. So the Lux collaboration is the current leader in their exclusion limits. So they've ruled out a large piece of the parameter space, and they're rapidly closing in on the neutrino background, below which currently they won't be able to see anything. And then there are a few claims of hints at detection, and there's this long-standing DAMA claim of an annual modulation that if you call it dark matter, sits somewhere up here. So the other one I want to draw your attention to is cogent, which is again seen in an annual modulation. So this is, they find an excess of events. There's the day of peak flux as the Earth goes with the sun around the galactic center, and dearth as it goes in the other direction. So that's a July max and a December min. So how do we get to this? We calculate some expected rate, fold in detector data, do some statistics, and I'll do my best to ignore the detector data and statistics today, and you can trust that it's done right, or you can go read about it. So what's the dark matter reaction rate? So there's all this particle physics stuff, and again, I'll do my best to ignore the cross-section as it changes with energy, the particle mass, and so this minimum velocity at a given recoil energy that a detector can see is important, and you'll see why later, but basically it comes into the integral. So there's also the astrophysics input. So this is just what they take. They assume a dark matter local density of 0.3 to 0.4 GeV per cubic centimeter, and that's pretty good. It has the advantage of, if that changes, it just moves all those lines up or down. So, okay, that's not terribly interesting. The escape velocity is a cutoff because, well, that's easier, right? And we don't expect much dark matter above the escape velocity anyway. And then there's a local dark matter velocity distribution, which is a really interesting thing. So what do they do for the local dark matter velocity distribution? Well, they take this Maxwellian velocity distribution with a particular parameter, so a peak parameter of 220, and that's what they all use. And you might ask, why would you assume it's a Maxwellian? Where do we have a single temperature from? Well, this is an integrable form, and they like it, and they all use it, so at least there's uniformity. I haven't seen any good physical motivations for it. Maybe someone here has, but you can share that with me after, certainly. Okay, so what else could you do? Well, you could go into the literature and look at many, many velocity distributions, choose one, but they're still being developed. So this was 2013. Mao et al. Suggested an exponential envelope. and they calibrated this against a suite of dark matter-only simulations. And that's really great, except that it's a suite of dark matter-only simulations, and that's not really what you want to use for the interior of the galaxy. So what have I done? We've got 4 Milky Way mass galaxies simulated with gasoline. These are dual runs in dark matter only and with the SPH. We have 170 parsec resolution. Right, the masses are between 0.7 and 0.9 times 10 to the 12 solar masses, so it's a narrow mass range, but they all have very different merger histories. So this guy's is continually bombarded. So again, range of merger histories. Surely they're not all like the Milky Way. This guy has a large major merger at redshift 1. This guy has its last major merger at redshift 2, I think, and is then very quiet. And this guy has a big 5-way merger at redshift 1.8 and a counter-rotating merger at redshift 1.4 that finishes up around 0.8, and you'll see the influence of those in just minutes. Right, so I go out at the solar radius in these galaxies, take a 1 by 1 kiloparsec annulus, and pull the dark matter particles out of there, and build velocity distributions. So in red is the dark matter only distribution on the left here. In black is the standard halo model. That's the same between both panels. In blue is the SPH dark matter distribution. Green is the MAU model with their fit parameters, and then the dotted lines are fits of those same distributions. So you can see why for a long time there was some worry about using the standard halo model. It looks nothing like dark matter only distributions, simulations. And okay, so there's a large dearth of high velocity material relative to what the standard halo model would have predicted. And we see that when you look at SPH simulations, there's not so much of a dearth in this halo, but still a deficit in our other 3. Right. So then the fits are much better, but okay, we've actually fit to our galaxy, so that's what you'd expect. But it's not only the galactic reference frame that matters, right? If you're actually planning on detecting dark matter, you want to boost to the Earth reference frame. So we've done that here. And you see that the dark matter only simulations continue to be bad, but there's quite some variance here. So this is due to that dark disk. It's co-rotating that comes in from that 1-to-1 merger. The counter-rotational merger produces some counter-rotating component and some co-rotating component. So let's get a step closer to the actual direct detection limits and show this integral. So you can see now this could have a huge effect where all of a sudden there's nothing, no expected rate in the simulated distributions, but there's a very clear signal from the standard halo model. And the black dotted line is a fit Maxwellian, and that offset is about the same as the offset between the day of minimum and maximum flux. So important for these annual modulation experiments, especially. And I guess I should say, so this axis really tells you how much a given detection collaboration probes of the velocity distribution. So Lux on their largest masses, I believe they get down to around a little under 100. So there's very well agreement all through there. But these low dark matter particle masses means you need a high velocity to see it. So that's where really all of this matters. Okay, and what impact does this have? So here are derived limits. So for Lux, there's a shift that gets much more dramatic as you get to lighter particle masses. For the cogent, again, a shift that's less systematic than if you were to look at dark matter only simulations. And there's much more variety, and this is because our Right? This, you care about where the dark matter wind is, and that direction changes in our SPH simulations, much more so than it does in the dark matter only simulations. And I think I'm roughly out of time, so that worked out better than I expected. Okay, so maybe I'll leave with the summary points and ask for questions.
Okay, questions?
So some simulations have suggested that there's a significant dark disk. That is, that there's an enhanced density of dark matter in the disk. You've emphasized the velocity distribution, but what about the density? These dark disks come, especially in simulations where there's a lot of accretion of small satellites, which, if they come in at a sufficiently small angle with respect to the disk, get torqued down to the disk and then deposit their dark matter in the disk. So it probably is important to have very good resolution to be able to see all these satellites in order to be able to answer that question definitively. And then it also probably depends on the merging history.
Absolutely, yes. Right, so as I alluded to, this is a resimulation of one of the prototype galaxies of the dark disk. And it does have, well, let me maybe show you the actual component distribution. So this is going around the azimuthal direction. In black is stars. This is that dark disk in blue. So the blue and red are dark matter distributions. Blue is for the SPH again. Red is for the dark matter. So I'm not, I guess, commenting on your physical scales. And okay, so what we see there is there's a slight enhancement, but it's not as dramatic, of course, as a stellar disk. It's much, much puffier. But in the original paper, really what was called a dark disk, as far as I can tell, is just that there's this huge co-rotating component. And there it is again in our other galaxy.
So you agree that it probably also depends on merging history?
Oh, absolutely. It's absolutely. Yes, very much. Yeah.
Quick question from Eric, just as we switch over the slides.
So you've made choices about the dark matter halo masses that you chose at the beginning. I've also presumed you made a choice about the circular velocity, or the velocity of the sun in the Milky Way. What did you choose, and what kind of difference would that make?
Right. Okay. So as far as the halo masses, these were chosen to be similar to one another and within the Milky Way's range. And there are two others that we had simulated that bracketed the range, and they don't change the conclusions. Though, of course, right, as you get to higher halo mass, your dark matter is going to move faster. So at the top end of the Milky Way mass range, it's really the fitted distribution that matters, and there's still the underprevalence of high velocity material.
Okay, let's thank Jonathan one more time.